This lecture is going to walk you through the F statistic in ANOVA as well as post hocs, what it means, and how we're going to calculate these. So far, our inferential statistics have mostly looked at comparing sample means to a predicted value or to one another. Now, I'm not going to be using correct null hypothesis statistics testing language here, so bear with me. Remember that according to null hypothesis statistics testing, each of our tests are assessing the likelihood of a sample mean occurring if the null hypothesis were true. So we assume that the null hypothesis is true, and given that, how likely is it that we ended up with these values? Although that is the proper way of talking about these tests, it's very convoluted and it can make it hard to keep track of the similarities and differences between tests. So for the moment, I'm going to put that aside. I'm going to talk about these tests more informally in a way that emphasizes the research question we might be answering with each of these tests. Now, we started out with one mean. For one mean, we were asking, is the population mean the same as the predicted value? And we tested this using a one sample t-test. We worked through the problems involving us knowing a supposed or a predicted population mean and determining whether or not our data matched up with the predicted value. Asking, do we have a full 2 scoops of raisins in our raisin bran? Then we moved on to two groups or two means. For this, we wanted to know, are the two groups the same or different? Are they from the same population or different populations? Most of the time, you will see this interpreted as the two groups are significantly different, which means they are from two different populations. Now, this can be two independent groups, for which you would use an independent samples t-test, or matched pairs, for which you would do a pair samples t-test. You can also look at the same people twice and ask if their scores at different times are significantly different, for which we would also do a paired samples t-test. But what about when we want to compare three groups or three means or four? What if instead of just testing a medication versus no medication, we wanted to test a high dose of a medication versus a low dose versus no medication? Or what if we wanted to compare students learning by just reading the textbook versus students watching online lectures versus students attending class in person? What if we wanted to compare customers' ratings of 4 different designs for a product? What if I wanted to know how a person's physical activity looked before, immediately after, and then each subsequent year after knee replacement surgery? My core question is still the same. Are the means the same or are they different? Let's say I have a bunch of patients with lower back pain and I put them into one of 3 conditions: physical therapy, muscle relaxers, or chiropractic adjustment. I want to know what their pain levels look like after 6 weeks. The question at the core of my study is, are there any differences between these 3 conditions? If the answer is no, the mean pain levels, the average pain levels, are the same for all 3 groups. If the answer is yes, then we need to know where those differences are. Was physical therapy better than muscle relaxers? Was PT better than chiropractic adjustment? And were muscle relaxers better than chiropractic adjustment? So for the 3 groups, we want to compare A versus B, A versus C, and B versus C. The test we use for multiple means is called ANOVA, or the analysis of variance. But before we get into that, we need to address the elephant in the room. Why don't we just do a bunch of t-tests? Why reinvent the wheel and use a whole different kind of test when we were getting so comfortable with the t-test? And the answer is, it comes down to type 1 error, or your likelihood of getting a significant result purely by chance. If you remember, we've generally been setting our alpha level to 0.05. Let's say our sample size is massive, like 2,000 people. So the t distribution is basically the same as the z distribution. I'm going to do this because I'm being lazy and I don't feel like looking up the critical value based on my degrees of freedom. And I already know that a two-tailed critical value for an alpha of 0.05 is 1.96 when it's a normal distribution. And the reason that I know it is 1.96 is because my undergrad stats professor drilled that into our brains. So my alpha is 0.05. My critical value is 1.96. The likelihood of me getting a t-statistic that is more extreme than 1.96 or negative 1.96 for the lower tail is less than 5%. But that's not zero. It's not impossible to purely by chance, completely randomly select a sample from the population and come up with a value at the very extremes of the population. An alpha of 0.01 instead of 0.05 would drop this likelihood to less than 1% instead of 5%, but that's also pushing our critical value out to 2.33 instead of 1.96. And it's also not taking that likelihood down to zero. A concrete example. You have a chart of the weight of adult cats, and it is a normal distribution. You have a mean and a standard deviation, and know that the 95% confidence interval for cat weight is from 7.5 to 14 pounds. So you pick up an animal at random. It comes in at 15 pounds. Now, according to our null hypothesis statistics testing, you would reject the null hypothesis that that animal you picked up was a cat because it is beyond the 95% confidence interval. You might say instead that it is a dog, but the animal is very much a cat. Remember that type 1 error is where we incorrectly decide that it is not a cat just because it's on those extreme ends. Now, we got kind of lucky there. We had a 5% chance of grabbing a cat that was outside those 95% confidence interval, and we managed to do it on the first shot. So let's be a little bit more realistic. We grab an animal and weigh it. It is between 7.5 and 14 pounds, so it registers as a cat. We grab another animal and weigh it. It registers as a cat. We do this over and over and over and over again. But even if every single animal in the room is truly and actually a cat, purely by chance, we should expect that 1 in every 20 animals we grab and weigh will come in outside of that 95% confidence interval and therefore be registered as not a cat, even though they are all cats. So the more tests we do, the greater the number of opportunities we have to get that 1 in 20 cat and to get a significant result even when there is no differences between our groups. That is what this comic over here, over on this right-hand side, is showing. In this comic, the scientists did an initial study. So I'll zoom in. There we go. They did an initial study. They found that there is no association between jelly beans and acne. And that makes sense. So they start out, jelly beans cause acne. Scientists investigate. So the scientists do the study and they find no link between jelly beans and acne. But they then wanted to look closer, and I hear it's only certain color that causes acne. So the scientists have to get back at it. So they do individual tests for each color. They test the purple jelly beans, no significant effect. Yellow jelly beans, no significant effect. Blue jelly beans, no significant effect. Red jelly beans, no significant effect. All of the colors show no association between jelly beans and acne, except for all of a sudden, they get to green. And the green one, right here, we found a significant effect. And of course, that is what the news jumps on. Green beans linked to acne because that's what popular press tends to do. But the problem is the more tests you run, the more likely you are to grab that really fat or that really skinny cat and say it's not a cat, or to find a significant association where none exists. Now, one thing, if you look at the number of tests they did on this, it is 4 times 5. That is 20 tests. So they did 20 tests. One of them came back significant. That is equivalent to the 5% chance of committing a type 1 error with using that alpha of 0.05. So how do we fix this issue when we do have multiple tests that we want to do? For example, if we want to compare multiple methods for treating depression or back pain, the answer is ANOVA. ANOVA is short for analysis of variance, but we'll get into what that means in a minute. ANOVAs are basically a way of testing for overall differences between multiple groups. It's a way to ask, are there one or more significant differences between any of these means? In other words, do all of these observations or scores come from the exact same population? Or do the data from at least one group seem to come from a different population? No, we are not yet looking for where those differences might be. That's coming in the post-hoc test at the very end. But we start out by asking, are there differences anywhere? And we do this by comparing the variability between the groups versus the variability within each group. Okay, so I do not at all like the way that the book explains the calculations for ANOVA. The author uses the computational formula, which is easier to compute by hand, but it really muddies up what you're comparing and how that's measured. So we're going to do this another way, using a definitional formula. We're going to start out with a really simplistic example. So we have three groups here, Group A, Group B, and Group C. Each group has 5 people, and you can see their scores listed. Just below them, so we have Group A right here, Group B right here, and Group C right here. Just below these, you can see the mean for Group A, the mean for Group B, and the mean for Group C. We can also see the standard deviation. Standard deviation for each one is exactly the same, 3.16. So although the means for each of these groups are different, the standard deviation's exactly the same. But you can see that the scores between the groups vary a lot more than the scores within the group. So there is no overlap between the scores for Group A, Group B, and Group C. And the standard error of the mean, the standard deviation of the sample means, is 10. If we look within Group A, we're ranging from a score of 21 to 29. So we have about 8 points of variation. We've got 8 points of variation for Group B and 8 points for Group C because I made this really easy on myself and I just made it odd numbers for each one. But when we look from Group C all the way to Group A, we're ranging from 1 to 29. So we've got now a full range of all of these of 28 points compared to just 8 for each of the individual groups. So the variability within Group A, within Group B, within Group C is relatively small, just 8 points. But when we put it all together, it's really big. So we're looking with ANOVA, we're looking at the variability within the group. So within Group A, within Group B, within Group C. This is our individual group standard deviation, and we compare that. So we've got our standard deviations here. We're going to compare that to the entire data set. Because we are going with the assumption that everyone in this data set from all 3 samples is from the same population. That is our null hypothesis. But if we look at the entire data set, all of these scores, our full data set standard deviation is 22. So that's a much bigger standard deviation than we're getting from the individual groups. Let's look here at an even simpler example. You have one person in each group who scores a 1. Person who scored a 1 in Group A, in Group B, and Group C. Person who scores a 3 in each group. Person who scores a 5 in each group, 7 and 9. The 3 groups are literally identical. There are no differences at all between the scores of the 3 groups. Now, we have the same standard deviations for each of the groups, just like before. But now you calculate the standard deviation for the entire data set, including all of those data points, and you find that your overall standard deviation is now 3.16. It's identical to the standard deviation of the individual samples. You can see this both in this example and in the previous one by looking at the range. So we were looking here, we've got a range from 1 to 8 for all of these. So we've got a range of 8 for all of these because the lowest one in group C and the highest one in group A is still a range of 8, versus the previous example where we had individual group ranges of 8, but from group C to group A, we're looking at a range of 28 points instead. So here we've got no difference. A range of 8 for individual groups, a range of 8 for the overall sample. So compared to that previous example where you can see that the within group standard deviation is much bigger, or it is much smaller than the overall sample standard deviation, here they're the same because our groups are identical. There is no difference between group A, group B, and group C. As opposed to here, we've got group A, group B, group C, and each of the samples has a standard deviation of only 3.16, but when we look at the full data set, we're getting a much bigger standard deviation. This indicates to us that there may be some sort of difference going on when we look at the whole sample. All right, now let's go back to the back pain example. We've assigned participants to one of 3 conditions: physical therapy, muscle relaxers, or chiropractic adjustment. We've tested them 6 weeks later to see how easily they can do everyday tasks. In this one, higher scores indicate being more functional, indicating that they have less pain. Lower scores mean their pain restricts their daily activities, so they're less functional. The best possible score on this measure is 30. You can see that our mean for physical therapy is 28, indicating that our participants who underwent regular physical therapy for 6 weeks overall doing pretty well. Our group that took muscle relaxers sitting here at a mean of 26. Still pretty good, though a little bit lower than physical therapy. Lastly is our chiropractic adjustment group. They regularly saw chiropractors and got their backs cracked, and their average score after 6 weeks was 23 out of 30. Now, it's important to note that just by looking at the descriptive statistics, we can see that it looks like there are some differences. However, we can't be sure whether or not participants in the muscle relaxers and physical therapy groups were statistically significantly different at their 6 weeks functionality, or if these are just random chance, if it is just a within the realm or within the range of what we would expect, assuming all 3 treatments are the same. Now you can see underneath these raw scores that I have for each of the groups, you can see that I have the standard deviation for each group. So physical therapy, we've got a standard deviation of 2.12. For muscle relaxers, we've got a standard deviation of 2. And for chiropractic adjustment, a standard deviation of 2. Underneath that is our standard deviation squared, which you will better know as the variance, because we're doing analysis of variance. So we've got a variance for physical therapy of 4.5, variance of muscle relaxers of 4, and variance of chiropractic adjustment of 4. Now, with analysis of variance, we're going to use the individual scores to calculate these variances for our sample means. Using some calculations that you'll see in a minute, we're also going to calculate the overall variance for the entire data set. I'll show you those calculations of how I got this in just a minute, but frankly, it's really easy and straightforward. In fact, you've done the vast majority of it already. Now, if all 3 groups are from the exact same population, the variability of the entire data set, all of these different scores, should be pretty close to the amount of variability in the individual scores or in the individual groups. And you can see that the overall population variance is actually, so we estimate it as 31.67, which I'll show you how we get those measurements in a little bit. And the average sample variance, which I just took by averaging these variances, is 4.17. So this overall variance looks way bigger than that average sample variance. So to recap, take the sample means, and we're going to compare those. We're going to use those, compare them to the individual scores to get those sample standard deviations and sample variances. We're also going to compare those individual scores to the overall mean and see how those vary and use that to get a variance for the overall population. So we can see that we have some pretty big differences here. When we compare those between groups, so between groups, meaning everyone all together, variability, compared to within groups, so these variances here, that is our within groups variability. We can see we have a pretty big difference here when we're comparing this between groups versus within groups variability. This tells us there's likely something going on between the groups that's creating more variability in pain scores than can just be accounted for by individual differences. When we have a significant difference in the amount of between groups versus within groups variability, that tells us that our groups are likely from different populations. But is the difference we see from between versus within statistically significantly different? That's where the ANOVA F test comes in. We evaluate whether or not our variances are significantly different using the F ratio. But what is this newfangled letter we haven't talked about before? The F statistic is similar to the T statistic and the Z statistic in that F is just another type of distribution that we're comparing our score to. F differs from T and Z because where Z just cared about your alpha level and T cared about your alpha level and sample size, more specifically your degrees of freedom, the F distribution varies based on your alpha level, the size of your sample, and the number of means or groups you're comparing. You'll also notice in figure 11.2 that it's also a different shape from the Z and T distributions. It's positively skewed, which means most of the scores are really close to zero and fewer are farther out. It also can only be positive. This is because if you remember, our standard deviation and therefore our variance can only be positive. So since the F statistic is based on your variance, it also can only be positive. Now it's called the F ratio because to get the value, we're comparing two different variances. We're looking at the ratio of the between groups variance and the within groups variance. Down at the bottom here, you can see one more way of viewing this ratio that might help make more sense about why F equals 1 whenever the null hypothesis is true. If our samples are all from the same population, F will be close to 1 or 1. If your group means are all identical, now your F will be 0. That's okay, doesn't mess anything up. It just means that the groups are exactly the same, but frankly, that's not very common. As you'll see once we start computing the different parts, the numerator is basically all of the variability, all the possible differences in the entire sample, including the differences that were caused by the independent variable, our group differences, plus the random chance individual differences. But what do I mean by differences? I'm talking about why we see variation from one score to the next. What explains why it is that one person scores a 20 and another person scores a 30 and another person scores a 24? What is it that goes into this? What causes that variation? Some of it, hopefully, is going to be caused by our group, by our independent variable or which group they're in. And some of it's going to be that chance variability, the error. Now, remember that in statistics, error does not mean mistakes. It just means individual differences in scores that we haven't explained yet. Because we haven't explained, and we're not going to explain, why some people in the physical therapy group scored a 25 while other people scored a 30. Why some people in the drugs group scored a 24 while other people scored a 28. So all of this, these individual differences here, get clustered into error. It's that random chance variability, it's just individual differences. So our numerator includes the group differences, so the differences that are caused by which group they're in, and all of the stuff that we're just going to classify as error. But that random chance variability also appears here in the denominator, which means if they are in both the numerator and your denominator, and you remember back to high school algebra, they're going to cancel each other out. And so all you get left with is the differences that are caused by our group assignment. Now, if there is no effect of our independent variable, there are no differences in our group beyond that random error, that random chance variability, then the IV differences become 0. So this becomes 0, and then you have this canceling out this, and that equals 1. That's why the null hypothesis is based on the expectation that our F score will equal 1. Going back to this back pain example from before, we have a certain amount of variability in scores from person to person. We can see this with the variances for each group. The group variances are greater than 0, which tells us there is some degree of individual variability that we are not explaining just by which group they're in. But we can also see there is variability in the overall scores for the sample that is much greater than the variability just from within the groups. This tells us there are between group differences as well. We can see these differences just by looking at the sample means. The group means are different, but we need to know if they're significantly different. Is the differences in the means between the groups big enough to overcome the variability within the group? Now, if the only variability that existed was individual differences, then our total variability would be pretty much the same as our within groups variability, but that's not true here because our groups are different. So we can see that average sample variability is 4.17. The overall variability is 31.67. This probably helps you see a little better what the book was talking about when they're saying that we're looking at between groups versus within groups variability. Cool, awesome. So we just need to get our variance between our groups and the variance within our groups and compare those. Awesome, cool. Unfortunately, calculating the between groups variability and the within groups variability isn't as simple as just taking the average variance or calculating the variance based on the standard error of the mean. Trust me, I wish it was, but it's gotta be more complicated than that because statistics. First, we have to start by calculating 3 different sum of squares terms. Now, we've done this before, way back at the beginning, remember? Sum of squares is just the third step of calculating your standard deviation. We're going to calculate some sums of squares. One for the between groups variability, group A versus group B versus group C, and one for the error, or within groups, and one for the total. Now, we don't actually have to calculate the total sums of squares, as you'll see, but it's a good way to double check that you're doing things correctly, because between groups plus error should equal total. Once we have computed the sums of squares, we're going to divide each of these, we're going to divide each of these by their respective degrees of freedom. And that's how we get our mean squares. Because remember, the mean is just the sum over the degrees of freedom. So we get our sum of squares, and then we divide it by the degrees of freedom to get our mean squares. And that's how we calculate our F statistic. Here are the 3 different sums of squares we're going to be calculating. We're going to calculate one for error, one for the total, and one for between the groups. Now, sums of squares for error, you have done this before. This is the same thing as the first few steps for calculating the standard deviation. You're going to compute the mean for each group and subtract each score from the group mean to get the deviation score. Square that to get your squared deviation, and do that for each score in the group. Then you're going to add up all of the squared deviation scores across all of your groups. In fact, you can see here in these slides from the Chapter 4 lecture on computing standard deviation, we calculate the mean. We subtract each score from the deviation right here. So we got a score of 12. Our average is 10. We get 12 minus 10 is a deviation score of 2. We square that, we get 4. We have a mean of 10. We subtract 5 minus 10. We get a deviation score of negative 5. We square that, we get 25, not 26. And then we're going to, so we do all of these squared deviations, and then we're going to take the sum of all of those. Now, we've already done this. So square the deviation, get the sum of squares. So you have done this. You know what you're doing here. The only difference this time is that instead of doing that for only one sample, you're going to do it for each of your samples using the group means for their respective group. It's as simple as that. The book makes it look really confusing because it keeps using computational formulas, which just make life difficult. Now, the sum of squares of the total is the exact same process, except that instead of subtracting individual scores from their group mean, so the mean for each group, we're going to subtract those individual scores from the grand mean. The grand mean is the overall mean from the entire data set, regardless of which group they're in. This is because, remember, we're assuming that everyone is from the same population. So you do the same exact steps as before, computing a deviation score for each person, but instead of using the group mean for each one, you just use the overall grand mean. Then you square those deviation scores and add all of that up for your total sum of squares. And then we're doing the sum of squares between. This one's a little bit wonky, but it still has the same basic steps. Here, instead of saying how much does each person deviate from their group or from their overall mean, we're saying how much did group A deviate from the overall grand mean? How much does group B deviate from the grand mean? And so on. And then you're going to multiply it times the sample size for your group. This is basically just giving extra weight to the groups that have different sample sizes. This is important because you often don't have perfectly equal sample sizes. So this is all it is. It's pretty straightforward, and now I'm going to walk you through how to do it in an Excel spreadsheet because we love our Excel spreadsheets. Here you can see my handy-dandy spreadsheet that I made to compute the F ratio for the back pain study. This will look very much like the spreadsheet you will use for the homework. If you want, you can even pause this video to download this exact spreadsheet from Canvas and follow along with me so that you can click on the individual cells and see the formulas that I used when making this. In the first column is the group identifier. So group A, group B, and group C. In row number 2, or in the second column, I have the raw scores from everyone in my 3 groups. In the third and fourth column, I've done the beginning of the standard deviation calculation. So I calculated each score's deviation from its group mean and then squared those deviations. So my first score here is a 25. They're in group A, so I subtract 25 from the group mean for group A, which is 28, and I get a deviation score of negative 3. I square that to get my squared deviation for person number 1 of 9. Same thing for person 2. 27 minus 28 is negative 1. I square that, and I get a squared deviation of 1. I do that for each of the scores in group A. Now I'm going to jump down to the first person in group B. I have a score of 24, and subtract that now from the group mean for group B, which is 26. The deviation score is negative 2, and I square that to get 4. I'm going to, person number 2, score of 24, subtract that from the mean for the group of 26, get a deviation of negative 2, square that, and get 4. I'm going to jump down to the first person in group C. I got a score of 20, The average for group C is 23, so I'm going to subtract that to get my deviation score of -3, square that, and I get a 9. At the bottom, you can see, so I've done this for each of these different scores, and you can see at the very bottom, I have added all of these up, so I get my sum of squares of 50. That is the sum of all of these individual deviation scores. So again, you have done this before. You did this way back in chapter 4. Now we're going to do the same thing for the sum of squares total. As I mentioned before, the sum of squares total is not strictly necessary to compute, but it is useful for checking your math. So I'm going to do the exact same thing to get the sum of squares totals, except that I'm going to use the grand mean, the overall mean for the entire sample, which I've calculated right here, rather than the individual sample means. So I am going to start with person number 1. I have a score of 25. I subtract it from the grand mean of 25.66667, and I get a deviation score of -0.66667. I'm going to square that, and I get a squared deviation score of 0.44444. Score number 2 is 27 minus the grand mean. I get a deviation score of 1.33333. I can jump down to the first person in group B. Now, again, I am treating everyone the same because we're doing the total sum of squares. So we're not going to do it based on the group mean. We're doing everyone from this grand mean because it is the total sum of squares. So we're treating everyone the same. So 24 minus 25.6667, I get a deviation score of -1.6667. I do that for each of these in group B, minus the grand mean. I do the same thing for everyone in group C, minus the grand mean, and these are my deviation scores. And then I'm going to square them just like before, and I add up everything to get my total sum of squares right there. See, so easy, so straightforward. It makes so much sense if you just use the definitional formulas instead of the stupid computational formulas that the book, for some reason, is trying to make you do. Finally, we're going to do the between groups, sums of squares. Now, if our samples are from the exact same population, all 3 groups are doing exactly the same, the sample means should all be really close to one another. And they look pretty different. Not huge differences, but they're kind of different. But we got to crunch the numbers. So, for our other sums of squared, I calculated the deviation, I squared it, I added it up. And we're going to do the same thing here. So this time I'm going to compare the means versus the grand mean. So it's basically the same thing, but now I'm going to take the mean for group A and subtract it from the grand mean. So I get a deviation score for the mean of 2.33333. Same thing for group B. I get the mean of group B, I subtract it from the grand mean, I get a deviation of 0.03333. Same thing for group C. Mean of 23, subtract it from the grand mean, and get a deviation of -0.26667. So we do the group mean minus the grand mean, and then what do? What do we always do to deviations? That's right, we square the shit out of them, and you can see that right here. We've got our squared deviation. So our deviation, square it to make these numbers. So you've pretty much the same thing for each of these. Get the deviation, square the deviation, add it up. So we get the deviation, we square the deviation, we add them up. We get the deviation, we square the deviation, we add them up. And here, we got the deviation, we squared the deviation, but we have an extra step that we have to do this time. For these sums of squares between, we have to multiply those squared deviation scores by the sample size for each group. So we are going to multiply this deviation score times your N for that group. Same thing. Deviation score here times the N, deviation score times the N to make that number. For example, if one of my participants in group B had just no-showed, then here I would be multiplying this times 4 instead of times 5, and so I would end up with 0.4 repeating instead of 0.5. And then once we have done that, we're going to add all of these up and get our sums of squares between. So we do the same thing as before. Each of these steps pretty much the same thing. Only difference is when you are doing the sums of squared between, you've got to multiply it times your N. To recap, sums of squared error. To recap, sums of squared error is just the individual differences from one person in a group to the other people in the group. It's that some people have a higher pain tolerance than others, might have had more severe injury than someone else, things like that. In contrast, the sums of squares between is going to focus on how each group differed from the grand mean at the group level. If everyone was from the same population, all of the groups were from the same population, no group differences between treatments, the group mean for group A would not vary very much from the grand mean. Same for group B and for group C. They would all be pretty close to that grand mean. But because we have these big squared deviations here, these comparably pretty big squared deviations, that tells us there's some pretty sizable differences between the groups. And that's what we're seeing in this sum of squares between. If there was no more than random variability between our groups, we would expect the sum of squares between to be pretty close to 0. What we're doing is we're seeing how much each group mean deviates from the data overall. I want you to think about this for a second. The error term is basically just the average variance of our separate groups. This is your everyday garden variety individual differences. But here we're looking at what the group does, what that between groups factor does. We're looking at how each of the means deviate from the overall sample. Now, if you look at our sums of squared error down here, which is 50, and you add that to the sum of squares between, which is 63.33333, you'll notice that this adds up to 113.33333. This tells us we did things right. The error plus between should equal total. If error plus between does not equal total, you messed something up. That's, for right now, really the only reason you need to know it. We might use it later to calculate the effect size, but when it comes to computing the F statistic, it's just to make sure that you did your math right. So now we have each of our sum of squares measurements, but we need to get the mean squares because the F test uses the mean squares, not the sum of squares. However, do we get a mean? Well, we add up our values and then we divide by the number of scores, of course. So we're going to do the same basic thing. We're going to divide our sum of squares by our degrees of freedom instead of the N this time. Now, you've had a few different ways of calculating the degrees of freedom already. For one sample and a paired samples test, it was just N minus 1 because you were estimating one parameter or one mean. For independent samples t-test, it was N minus 2 because you were having to estimate the means for two separate populations instead of just one population or the different score. But now we've got more tests that we're doing. Here we've got a couple of calculations for degrees of freedom. You need both of them. You need both the between and the error to find your critical F value. The first degrees of freedom is for the numerator, or the between groups estimate. For this, we're going to use K minus 1. K is going to refer to the number of levels or groups that we have, the number of conditions that we're testing. Here we have 3 different groups in our study, so k is 3. Therefore, the degrees of freedom for our numerator, or the degrees of freedom between, is k minus 1, which is 3 minus 1, which equals 2. Remember, the error term is all about individual variability. So naturally, our degrees of freedom for the error term will also be based on the total sample. But instead of subtracting the constant, like 1 or 2, from the total sample size like we did with t-test, we're subtracting k, or the number of groups, from the total sample size. So we have 15 participants in our study and 3 groups, and so we're going to have 12 degrees of freedom for our error term. Lastly, we have the degrees of freedom total, which is our overall n minus 1. You really don't use the degrees of freedom total for anything, but it is useful because just like how the treatment and the error sums of squared added up to equal the total sums of square, the same thing is true for the degrees of freedom. So 2 plus 12 equals 14. We now go ahead and plug our sums of squares from the spreadsheet and the degrees of freedom into our mean squares terms for the between groups in the error terms. So we go back to our spreadsheet and we can grab those between sums of squares, which was 63.33. So if we go back to that spreadsheet, we had our between sums of squares, 63.33. We're going to go ahead and put that right here. We've got our degrees of freedom between, which we just calculated. That's going to be 2. And then we're going to do the same thing for the error. So we're going to pull our sums of squares for the error, which is 50, and we're going to divide that by our degrees of freedom for the error, which is 12. So we're going to divide those. We get 63.33 divided by 2 is 31.67, and 50 divided by 12 is 4.17. We can already see that our between subjects, our between is much bigger than our error term. So that 31 is much bigger than 4. But we're going to plug these into the formula for our F ratio. Now, if you were paying attention, if you're paying close attention, you probably noticed that 31.67 and 4.17 were the exact numbers that I was using way back at the beginning. 4.17 is actually the mean squared error, but it also happens to be the average of the variances that we were looking at earlier. So you might be saying, why don't we just compute the variance for each sample and take the average? But it doesn't always turn out that way, especially when you have unequal sample sizes. So it is important to take the full steps and not take shortcuts, because the shortcuts don't always work. This one just happened to. Finally, pretty much the last step, we're going to plug those mean squared between and the mean squared error into the F ratio formula. So we've got the mean squared between over the mean squared error. So we've got our 31.67 over 4.17. That gives us an F obtained, an F ratio of 7.60. Now, this is quite a bit bigger than 1. Remember that if the different groups had no effect, if there was no impact of which treatment group they were in, the F would be pretty much equal to 1, because the top and the bottom numbers would have been pretty much the same, because there would have been very little additional effect of that between subjects, that between groups effect. But that is clearly not the case here. Remember that our between groups variability, that numerator, does include both the differences that are caused by the group assignment, as well as that random chance variability due to individual differences. But because we also have those individual differences measured via the average sample variance, that error term, it cancels out. And all that we're left with is the between groups differences. Now, all we have to do is go to our F table, use the between and error degrees of freedom, and find that critical value to determine whether or not to reject the null. So when you look at the F table, you'll notice that it looks a bit different from the Z and the T tables. That's because instead of just having one value for those degrees of freedom, now we have two. So you're going to have the numerator degrees of freedom along the top here, and the denominator degrees of freedom along this side. So our degrees of freedom between, so that numerator, is 2. So we're going to go to this 2 column right here for our numerator degrees of freedom. And our error degrees of freedom, our denominator, is 12. So we are right in this box here. Now you can see that we have 2 numbers to pick from. One in this normal light font and one in bold font. And if you look way up at the top, you can see that the textbook author mentions that the light face type is for an alpha of 0.05 and the bold is for an alpha of 0.01. We're going with an alpha of 0.05, which gives us a critical value of 3.89. Now, going back to our F statistic, we had 3.89 as our critical value, but we got an F statistic, an F ratio of 7.60, which is well above that critical value. So we can say that we have a statistically significant difference. Yay! And back full circle to the raw data. Here we are. We can see these raw scores. We can see our original means and standard deviations and variances. And at the bottom here, we have the proper way to format the F statistic in our when we are writing up the results. So unlike the Z and T tests, you now need to include 2 different numbers for the degrees of freedom. This is because finding the critical value for our Z and T tests only required 1 number for the degrees of freedom to locate, but now you need both, so you have to report both. So you put your italicized F, you put both of your degrees of freedom, the computed F statistic, and your p-value. Now what this tells us is that there is a significant difference somewhere. At least one of our groups is significantly different from at least one other group. But the F statistic does not actually tell us where the differences are. It might be that physical therapy was significantly better than muscle relaxers and chiropractic adjustment. It could be that physical therapy and muscle relaxers are pretty much equal, but they are both better than chiropractics. It could be physical therapy was better than chiropractics, but that muscle relaxers were pretty much equal to both physical therapy and chiropractics. Not significantly different from the other two. The F statistic does not actually tell us where the differences are. All it tells us is that there is at least one difference somewhere. To find out which groups are different from one another, you have to do what are called post hoc analyses. Post hoc means after the fact, because what we're doing is first we have to determine whether or not the F test is statistically significant. If you do not have a significant F test, you cannot go on to do the post hoc analyses. It is not good statistics. It does not matter how big those differences are. If your F test is not statistically significant, you cannot go on and do your post hoc analyses. So post hoc means after the fact. And a lot of times we will refer to these also as pairwise comparisons, because what we're going to be doing is we're going to be taking pairs and evaluating those pairs and seeing, are those pairs significantly different from one another? You can kind of think of these as individual t-tests, but accounting for that extra alpha that we need to consider because we're doing these extra tests. So it's correcting for what is called the experiment-wise alpha. because we're not just running one comparison. We're not just comparing PT to chiropractics. We're comparing physical therapy to muscle relaxers, physical therapy to chiropractics, and muscle relaxers to chiropractics. We're doing 3 tests instead of just one. So we need to correct for that. We need to account for that difference when we're looking at those critical values, and making sure that we're not leaving ourselves open to coming up with those chance occurrences, and running risk of running into that. The most common correction that we use is what's called the Tukey's Honestly Significant Difference, or HSD test. This is a statistical correction. It just slightly modifies the calculation in order to correct for that extra alpha of running multiple tests. So the way that you're going to do this is there are a few different ways that you can calculate this. The way that the book has you do this is a few different steps. So you're going to compute the group differences. You're going to take the mean scores and you're going to subtract one mean from the other. You're always going to start with the larger one. You're going to subtract the larger one from the smaller one from the larger one. You're going to then locate the critical value. Now, the critical value is going to be dependent on a couple of different characteristics, including the N for your samples and the degrees of freedom for your error. So that DF error calculation that we already did. So your 12 right here that we've already done. You're then going to compute the Tukey's HSD value, and then you're going to compare your computed score to those group differences that you calculated. So step 1, again, we compute those differences. So we have physical therapy versus drugs is 28 minus 26. So we get a difference score of 2. Same thing for physical therapy versus chiropractics. We get a different score of 5. And then drugs versus chiropractics, we get a different score of 3. Then we need to locate our critical value. Now so this is the calculation for the Tukey's HSD. This QA is going to be our critical value. So we need to find this using what is called the studentized range table. For this, we need 2 different values, just like we had 2 different types of degrees of freedom for the F test. We need 2 different values for the studentized range table. So you can see along the top here, we have the range. And over here on this column, so this column right here, we have our degrees of freedom of the error. So our range, in this case, the range is the number of groups that we have. So we have 3 groups, so our range is 3. The degrees of freedom error, we already calculated. We already looked at that. Degrees of freedom error is that total N minus K, so that our degrees of freedom for the error is 12. So we're going to go over to this table. Our range is 3 because we have 3 groups. Our degrees of freedom error is 12, so we're going to be in this box right here. Again, this is the same thing in terms of bold that we saw in the F table. So this 3.78, that's going to be our 0.05 alpha. If we wanted to go with 0.01, we would go with 5.05, but we're going with alpha of 0.05. So our critical value is 3.78. So now we're going to go over here. We're going to plug this in. So we've got our critical value of 3.78 that we just looked up, and we're going to multiply this times the mean squared error over n and the square root of that. So we can go back over and we know that our mean squared error right here is 4.17 because we already calculated that. So our mean squared error, 4.17, and then our n so the n is going to be the n for the sample size for each of these. Now, This is an important consideration because this assumes, the way that this test is done, it assumes that your N is going to be equal for both of your groups. If you do not have this, if you have unequal sample sizes, you have to modify this equation a little, but we're not going to worry about that because frankly, you're never going to have to do this by hand in your life, but it's important for you to understand the basics of it. So we find our critical value, 3.78. We take our mean squared error. We take our N for the PT group and the drugs group. Our N for each of those is 5. PT versus chiro, their N for each of those is 5. Drugs versus chiro, N for each of those is 5. So we're always going to put 5 down here. So we multiply mean squared error by, or divide mean squared error by the N. We take the square root, we multiply it times 3.78, and we get an HSD score of 3.451. We then compare this to our different scores. So 3.451, drugs versus chiropractics, that is not greater than this calculated value. So drugs versus chiropractics, not a significant difference. Physical therapy versus drugs, not a significant difference because it was only 2 and our critical value is 3.451. But physical therapy versus chiropractics, our difference score was a 5, critical value is 3.451. So that tells us that because we had this significant F score right here, we know that there was at least one difference somewhere. And based on that post hoc test, we can say that chiropractics and PT were significantly different from one another. However, drugs and PT, not significantly different. Drugs and chiropractics, not significantly different. But this is where we saw that significantly different effect. And this is why you can't just go based on the F test. You have to also do the post hoc analyses in order to see not just is there a difference, but where is that difference? All right, so this sums up ANOVA. You can also do effect sizes, which the books talks about, but this is basically the gist of how you do these one-way between subjects ANOVAs.